Hello everyone, welcome to my channel. So in this video, I will continue my introduction of probability. So in our previous emails, we already talked many things about what is a probability and some important terminologies in these topics. And in last video, we already talked about what is a probability, probability mass function and cumulative distribution functions. They are all the way to describe something about the discrete random variable. So now, start from these videos, I want to introduce some classical and also important distribution of our discrete random variable. So in this video, I want to talk about a binomial distribution. So before we introduce the definition of binomial distribution, let me first talk about one terminology. What is Bernoulli trio? So Bernoulli trio is a special trio. It means for this one, we can only get two possible outcomes. So for example, we always use this example, like we flip a coin, right? And then we can have two possible outcomes. We get a head or we get a tail. So in this way, it means flip a coin is a Bernoulli trio. And also you can think about some other example. For example, if a student take an exam, then there are two possible outcomes, fail or pass. So if we focus on possible results like fail or pass, then this is also a Bernoulli trio. And for this example, you can know the result of an exam. This can be so many different ways to describe it, right? For example, we can think this is get A, B, C, or maybe D or F, or we can describe this more in detail, like A plus, A minus, or maybe we use the score, like 79, 78, 98. So based on the different way we describe the result, actually this will change this experiment is a Bernoulli trio or not. So here, to use this as a Bernoulli trio, the only thing we need to careful is we have two possible outcome of this experiment. Okay? And then, so after we have this definition, then we can describe what is the definition of our binomial distribution. So binomial distribution is a random experiment consists with n Bernoulli trios. And this means our experiment will satisfy the following three requirements. So the first one is all the trios are independent. And what this means? This means, for example, if we have one random experiment, which means we flip three coins, and then if these are independent, it means no matter what result or outcomes we get from we flip the first coin, we will flip the second coin, and then the probability or the possibility of we get a head or tail is now depends on the result of the first one. So then we flip a three coin consecutive, then this means it's independent trio. However, if we say, okay, we have three coin, we flip it, and whenever we get a head, we will immediately stop. So in this situation, it means it's not independent, because if we flip the first coin and get a head, we won't flip the second one. So that means these trios are not independent. Okay, and the second requirement is each trio results in only two possible outcomes. And here generally we label them as a success or a failures. So this is just a more abstract way to describe. Here we only have two possible outcomes. And the third thing is the probability of a success in each trio remains same. And generally we denote this by a small letter p. Okay, so that means here, if we flip three coins, then if all of the three coins are fair one, so that means they also have 0.5 probability to get a head and the same one to get a tail. Then these three coins should be all fair one. However, if one of them is a best cone, so maybe it means we will get higher chance to get ahead. Then we also say we flip the 3 cone independently. It now means this is a binomial distribution because the probability of the succeed get ahead is different. Okay, so this is 3 requirements of our experiment to become a binomial distribution. And then to say a distribution, right, it means we use this way to describe our random variable. So here, the first thing we need to do is what is the definition of our random variable. Then we can get our random variable is the number of succeed in this binomial experiment. And then here we can denote this by the bin and with a parenthesis n comma p inside. So here we call x is a binomial random variable, and here what's the meaning for n and p? So n is how many Bernoulli trio we have. So if we flip 3 cone, and then it means here n is equal 3, and p is the probability of we get succeed in each Bernoulli tail. So for flip a cone, it means we get one height is 1/2 when we flip 1 ferro cone. Okay, and so here, based on this requirement, it means for our p and n, we'll have this requirement. So p, because it's a probability with some possible like succeed, probability of succeed. So it's a number between 0 and 1. So this is based on our property of probability. And for n, it means here at least we should have 1 Bernoulli tail, right? And it can be 2 or 3 or any integer number. So this is how we can, what is a binomial experiment and what is a binomial random variable. And then what is a binomial distribution. So the way we can describe a distribution is by a PMF, probability mass function, or by a CDF, the cumulative distribution function. So here let me give you what is our PMF for the binomial distribution. So then we can denote the PMF of this binomial random variable as this equation. So here actually we can see the first term in this equation. Here this one actually is a combination here. So it means we select x of objects from a total n different objects, and we don't care about the order. So it's an unordered arrangement here. And here, in fact, depends on the textbook you use. We have 2 methods to denote the combination. We can use this C super n sub x, or we can use a big parenthesis to put n on top and x on denominator. But no matter what's the meaning of these 2 symbols, what's the symbol you use, the meaning of them is exactly same. So that all means here we have the n factorial divided by x factorial, and then n minus x factorial on denominator. That all the meaning of the combinations. So if you don't know what is combination, please look at my previous videos. And then it's about we times x to p to x power, and 1 minus p to n minus x power. Okay, and here for this combination here, in fact, because this is very important in our binomial distribution, so sometimes we also call this binomial coefficients. Okay, and then if we have a PMF, then of course, based on this PMF, we can compute a CDF, right? So then what's the CDF of this binomial random variable? This is just based on the definition of our PMF and CDF. So here, based on this definition, we have the CDF at x is equal the probability when our random variable is smaller or equal to x, and this is becomes the sum up of our PMF at value xi until the xi is smaller or equal to the upper to x, right? So this is the meaning and the way how we can compute CDF for a random variable. And you can see for if we have a question and how to get the PMF and CDF of a binomial random variable, it's not so easy. The equation looks kind of very complicated. However, binomial is a really important distribution in probability. So here, let me give you two more property of our binomial distribution. They are the mean and variance, or in other words, they are the expected value and variance. So here, let me give you the equation. It's like this. So the mean we can denote by mu or ex. So if you're not familiar of the definition of mean and variance, you should look at my previous video. So the mean of our binomial random variable is n times p, and then the variance is equal to n times p times 1 minus p. Okay, and then if you're familiar with the standard deviation, because the standard deviation of one random variable is equal to the square root of our variance. So that means here you can have the sigma of our standard deviation of this random variable is equal to square root of n times p times n up 1 minus p. Okay, so now let me solve one example for you. So this example is about a multiple choice test. So assuming this test, we have 6 unrelated questions, which each question contains 5 options. And assume there is a student who will randomly guess the answers. And let our random variable be the number of correct answers he or she gets. Then the first question is what is the probability of x equals 0 and what is x equal 4. Okay, so here before solving and let tell you what is the formula we should use, let me explain a little more about this question. So in this question we have some information here. For example, we have 6 questions, each of them have 5 options, right? So this of course is some numbers we will use when we decide which formula, and then we should plug in this value into formula. However, there is also other 2 important items. The first thing is unrelated question. So why in the question they say unrelated question? So this is because if we look back our definition of Bernoulli distribution, the first requirement is we have some these Bernoulli trios are independent. Okay, so this is a first requirement to get a binomial distribution. So here in this example, they said they are unrelated questions. So it means if I make a wrong guess of the answer for the first question, it won't affect my answer for the second one will be correct or not. So this is to make sure our experiment is satisfies the first requirement of binomial distribution. Okay, and then the second important thing is they say this student is randomly guess the answers. So when they say randomly guess the answers, in other words, they said the probability we will get one option or guess one answer among these all 5 options in each question is equally likely in ones. So that means here for each of the, no matter A, B, C, D, or E, we will have 1/5 of the probability to guess that's the correct answer. And because the student is randomly guess all the answers, so that means for each of these 6 questions, the chance we will get a correct answer is all 1/5. So in other words, this is satisfies the third requirement, like we will have all the probability of a correct answer is same, that all 1/5. And also here for our definition of this random variable is the number of correct answers. So that means now for this each guess we only have two possible outcomes, a correct answer or incorrect. So that means although our choice is among A, B, C, D, and E, but by this definition of our random variable, actually we divided the possible outcomes to two groups, correct or incorrect. And in other words, now when we guess the answer for each question, it's a Bernoulli trio. And also with the previous two requirements, unrelative and randomly guess, we can have this is a binomial random variable. Okay, so now based on our analysis of this question, we can say here x is a binomial random variable. Then the probability of x equals 0. Actually, this is a part of our PMF, right? Because PMF of a random variable means the fx here is equal to the probability of our capital X equals small x. Right? This is the meaning of our PMF. So in other words, what we have here, we will have this part, this equation, x equals 0, this probability is equal our value of our PMF at 0.0. So in other words, what we need to do, we just need to write down the formula of our PMF for a binomial random variable, and then plug in all of the value we need here. So here in this part, what we have for each of this trio, this is a one of our one Bernoulli trio. So that means here for our n, because we have total 6 questions, so that means here n is equal 6. And then what is our p? This is a probability to get a succeed. And here for our success is get a correct answer. And because we randomly guess the answer, so that means this is 1/5. Chance of probability is 1/5 for us to get a correct answer. And then the last thing is about what is a small x. So small x is here what we have in this value, right? We try to find the function at 0.0. So that means here, of course, x is equal 0. Okay, so that's what's the value we need to plug into this formula. So now we only need to plug in them. So we have 6 and 0 in the random coefficient, binomial coefficient, or in other words, the combination here. And we have 1/5 as p, and we have 1 minus 1/5 to n minus x, so it's 6 minus 0. Okay, so this is what we need to plug into this formula. And then the other thing is you need to compute this one by your calculator. So here I just give like how you can compute this one, but the answer of this part is equal 0.2 and 0.26. Okay, so this is the answer for this part, probability x equals 0. And then for the probability x equals 4, all other things are same with the previous part. The only difference is now we care about the value of our PMF at 4. So then here in this case, it means for our n is still equal 6, p is still equal 1/5, but x now is equal 4. So based on this one, we can also plug in all the necessary value into our formula, and then we will get our answer of this question is equal 0.02. So you can see this is a very small number. So that means if we have 6 questions in our test and a student just don't know anything about the question, just randomly guess the answer, so there is only 2% chance the student can have answer get a 4 or 6 points for this question. So this is a very small number, to be honest. And then this is a part 1 and then part 2. So let us compute this one. So here the question is asked us what is the CDF's value at 3 and what is the probability was x be larger than 2 and smaller or equal to 5, and what is the probability our x is greater or equal to 4. Okay, so first for this CDF at 3. So here by the definition of our CDF, we know this 3, actually we have the formula for this, right? So you can use the formula directly from our previous equation here. So this is, we can just plug in the equation here by a sum of a combination of xi smaller or equal to x and then about all other terms. And also the other way is like similarly, but here by the definition of our CDF, the value of our CDF at 3 is equal to the sum up of our PMF plus until our value of 3, right? So this is also other way to compute this. So here, for each of this PMF, you need to use our method in previous part 1 to compute each of them. But here I just skip this part, but I just give you an answer so you can try this by yourself. We will sum up this 4 numbers, and then the final answer is 0.98. Okay, so this is what we have for this part. And then the question for probability 2 small or equal to x smaller or equal to 5. So for this one, there is what we can compute. Is actually we can just compute this by our definition of PMF. So here, what's the possible value for our x between 2 or 5? So the possible is we get a 2, and we get 3, and 4, and 5, right? So that means, in other words, we will sum up the PMF at value 2, 3, 4, and 5. And then you should, for each of the PMF, you need to use our technology in previous part 1 to compute them. But here I just give you the final answer is 0.35. And then for the last one, about x is greater or equal to 2. Now the possible value we can have is we can have guess 4 question correct, or guess 5 question correct, or guess all of the question correct. So then this is a way we can compute them, and then this is one way we will get our answer. So the answer will look like this. But we also have another way to compute this. So this is, we can use the 1 minus the other chance, right? So it means 1 minus the PMF at 0, 1, and 2, and 3. So because the only possible outcomes in our sample space here is actually we have 0 question correct, 1, 2, 3, 4, 5, or total 6 question correct. So that means the probability of the event have x larger or equal to 4 is an exclusive, mutually exclusive event for the event x is smaller or equal to 3. So that means we have 2 ways to compute this one. Okay, and then the last part of this question is about what is the mu and what is the sigma square of this question. So that means what is the mean and what is the variance of this question. So now what we need to do is just we can use the formula. So the mean of a binomial distribution is equal n times p. So here in total we have 6 questions, n equals 6, and p is equal 1/5. So that means for our mean of this binomial random variable is 1.4. And for our variance sigma square, this is equal n times p times 1 minus p. Okay, so then by plugging in all value of this part, we can get the answer of this question is equal 0.96. Okay, so this is our example of this binomial distribution, and hopefully you have a clear idea of how to decide this one experiment is a binomial experiment, and how we can decide one random variable is a binomial random variable. So in my next lecture, I will talk about the geometric distribution. So geometric distribution is also a very important distribution in discrete random variable. And please subscribe my channel, and see you in my next lecture.